All right. Actually, I should probably move my mic closer. Are we live? Twitch seems to say I'm live. Is there audio? And there's audio. All right, sweet. All right, welcome to this week's office hours on kernel security. All right, let's just jump straight into it. Are there any questions, or what are the immediate pressing questions? I have some ideas on some things I can demonstrate in regards to scripting solutions within this VM context. But let's see here. I know that someone had already asked me to discuss 9, but I guess I'm kind of curious how far are people already into this. Okay, people are definitely making progress with trees going through and solving them all through the night. Pretty crazy. It's definitely a surprise to see them already all solved, considering 9, the one that someone had a question about. The technique for exploiting it, I don't think is currently covered in any of the lectures or extended Q&A yesterday, and something that's planned, of course, to be discussed in a lecture that hasn't yet been recorded, and also the next extended Q&A. And I guess I'll also talk about level 9 in my office hours today, since there are people already stuck on it. But yeah. Okay. Looks like someone is on Rev 19. Yeah, that's probably one of the more likely challenges to get you stuck on solving things. Oh, Zero's in the chat. Hello. I saw that you posted something about kernel exploitation. That's seems to have lined up exactly with when we launched kernel stuff. That's cool. All right, let's see here. What do we want to do? Let's start by just quickly going over the setup of the challenges here. For anyone kind of still stuck, I know in the Discord there were definitely tons of questions about how do we get started with this kernel infrastructure, basically. And I guess I can jump into that. Yeah. Okay, so if I start level 1, we'll just start with that to make it simple. And in this case, I just started it in practice mode. There are some differences between starting it in practice mode and not starting it in practice mode that extend beyond just the standard sudo versus non-sudo distinction here. And the primary thing that's going to happen when you start up in practice is when you launch up the VM, it's going to launch up with this -s flag on QEMU. And that -s flag is going to make it so basically you can GDB into the kernel or into this VM. Okay. So if we want to start these challenges, we're going to see that inside of challenge, at least on level 1 and most of the kernel levels, you're going to see that there is just a .ko file. And if you try to treat this like other challenges and you try and run this .ko file, it's going to tell you no. Yeah, so the .ko file is not just like this default, normal executable file. There's a question in chat. Why did you guys decide to hide the solve list for each challenge? It wasn't an intentional hiding of it. It's just as a result of us retheming things so that there wasn't just a wall of every single challenge like it was last year. The solve list got lost in that transition. I mean, maybe eventually we'll bring that back. But you can technically, if you really wanted to know who solved what, you could in theory click on every single user, write a script for it. The data is all publicly there. When you click on someone's profile, it shows all the challenges they've solved, but not a great interface, I can agree. Okay, so this is not a standard binary, as I was saying. It is a relocatable. So for instance, if we look at bin false, we're going to see that this is some dynamically linked and that it has an interpreter associated with it, where the interpreter is LD, and that's what allows you to, for instance, run bin false without issues. On the other hand, if we, I guess just to kind of go over elfs a little bit here, if we look at something like libc, actually libc is runnable. Yeah. If we wanted to look at that though, libc 231.so, you can see it's also this dynamically linked. The thing is, it has an interpreter with it. What is not runnable? LDD user bin tmux, that's gonna have something that probably is not runnable. I assume this is not runnable. It's not executable either. If we look at this 231.so, you're going to see that it doesn't have an interpreter associated with it. So even if we run like LD that, it doesn't have an entry point. This is not meant to be runnable. You know, most libraries are not runnable things, and in much the same way, moral of the story, this .ko file is not runnable. Okay. What this .ko file is, the convention is that a .ko file in Linux, the KO I believe stands for kernel object, and it's meant to be inserted into the kernel. And it's basically going to be some code that's residing now in the kernel. In some sense, it's like a plug-in for the kernel, if you want to think about it that way. Okay, so if we want to actually insert it, the normal way we would do that is we would use this command insmod. So we would do insmod challenge baby kernel level 1.ko, and it would be inserted into the kernel. However, there's two reasons that we can't do this. The first one is that you must be root in order to do this. And the second one is that we are currently, so if we were root, for instance, sudo insmod, that's also not going to work. The reason that doesn't work is because we're currently residing in this non-privileged Docker container. And the way that all of these containers work, that setting up all of the challenges, right? Your challenges are in your workspace is all inside of these containers. And these containers are all effectively connected to the same exact kernel. So all of your containers are separated, but they're not separated by having separate kernels. So somehow we let you actually start inserting kernel objects into the kernel, you would be affecting the kernel that everyone who's using the system, they would all be affected by that. And it would be a complete nightmare and would not be good. So moral of the story is that we have VMs for dealing with this, so that you can basically spin up a VM that's going to have an isolated kernel, and that is why these challenges are all different like this. Okay, so if we run VM, we're going to see that this is just like a command that resides in your path. And if we do vm-h, it's going to kind of do at a high level some examples about all of this VM stuff. So these are the commands that it exposes. We have the ability to connect to a VM. We have the ability to exec, which we'll talk about in a bit. The ability to start the VM, stop the VM, restart the VM, debug the VM, and this is where we're going to do a GDB attach. And then we have build, which can be useful if you want to kind of experiment with some kernel modules. You don't really have to use this at all, though, in the challenges. And then logs. Okay, so let's start by doing VM start. And then if we run VM logs, we're going to see that this VM is booting up. So if you've ever set up kind of like a Linux environment that's running in kind of like an Ubuntu server edition, you would see these crazy messages going through as the kernel is booting itself up. And that's what we see here. And the way that these challenges work is that the entire file system of your container is shared with the file system of this VM. You're operating on the same file system. And it recognizes, as part of the boot up and the way that we have this all configured, that there are these challenge.ko files, and we're automatically inserting those into the VM. And that is what's producing this text. That .ko file has some logging associated with it when it gets inserted into the kernel, and it prints out all of this text. So it says, welcome to this kernel challenge. So that is where the welcome message has suddenly moved to, right? We don't have this binary that you're going to be able to run, but we still want to welcome you to the challenge. So the way that we can do that is we can welcome you in the logs. Okay, so that's kind of the high level description of all of this. So it tells us this challenge will misuse the kernel in a way that will teach you about basic kernel exploitation. All of these challenges, I believe, yep, all of these challenges have a simple character device interface. So basically we have this pwn.college file, and that is effectively how we're going to interact with the challenge. And in this case, we can open, read, write, close this device as you would any other file. If you can figure out the password, the character device will allow you to read the flag. Good luck. Okay. So it tells us we have this proc.college file. However, we're not currently in the VM. If we do ls-al proc.college, we're going to see that that file does not exist. How can we make that file suddenly exist? Okay, the way to do that is to run vm connect. So we can see right now that we are hacker at practice baby kernel level 1. When we do vm connect, that's going to change. What we're doing is we're SSHing into the VM. And suddenly, rather than being practice baby kernel level 1, we are VM practice baby kernel level 1. So now we are in this VM. If we want to just kind of quickly examine the file system, we can see, for instance, /flag still exists. Challenge still exists. Everything still exists. We're on the exact same file system. It's just now we're in a VM, which means that now we have a separate kernel. And with this separate kernel means we can start inserting the challenges into the kernel. Okay, so that is how that works. What else? Okay, and now, I think it's the important thing, is now we have this proc.college file. This suddenly exists. And it's important to note that in this case, and for most of the challenges, but not all of them, this proc.college file is read, write, read, write, read, write, read, write. So most importantly, the other group, because we're not root, is able to read and write to this file, which means that if we do, trying to think how to show this. So we can do cat proc.college. This is going to be kind of a nightmare, but we will do it anyways. We're going to see it spams us with this password description forever, kind of in the same way that if you cat devu random, right, it just goes for forever. Clear reset. But another way that we could do that is we could do I wish I knew how to use this off the top of my head. Oh, whoops. proc.college of equals dev standard out. Count equals 1? No. Do we need dev standard out? So that read in. Proc self fd1. Okay, sure. Okay. Basically what we're using is we're just using the dd command to perform just a single read syscall, whereas cat will theoretically keep reading until it thinks that there's nothing left to read, but because it's this device file and there's always more to read in the way that this is implemented, it's a little bit nicer to use dd. Alternatively, we could probably be less insane and not figure out how to use new tools, and we could just run Python. You're going to notice that some things are a bit slower. So if I run IPython, it's going to take a bit for this to load up, and we'll talk about how you can kind of get around having to deal with that. But just for demonstration purposes, we will sit here and wait for IPython to launch. And the reason that this is slow is that it's all running within QEMU and everything's being emulated. Unfortunately right now. In a future edition of this, we will probably be able to do this stuff fast. We'll use dev kvm, but that's a different issue. Okay, so IPython finally booted up. Import OS, and then if we just do OS read OS open pwn.college, open it for reading, and let's just read 100 bytes. And of course we will see, yep, here's this password thing, because we just did one read syscall. So we can see here in the context of this challenge that it's doing this. If we look at the logs, so for instance, if we hit Control D to leave, maybe we don't want to do that. Let me switch over to another terminal, which is not in the VM, though we could do it also within the VM, doesn't really matter. But if we run VM logs, we can see that there's all sorts of logging happening. And this is whenever the device read, basically whenever we're doing a read to that pwn.college, it's logging information about that. That's kind of what the .0 version of the challenge is going to do, is kind of print out all sorts of random debugging information. Yeah, okay, so I think that is enough of a description of how all of this works if that's where you're stuck. Okay, and I guess just to show a little bit more specific to level 1, if we did something like os.write, so it told us that we're allowed to write to this thing as well, and that isn't always necessarily the case. A character device doesn't have to make it so you can open, read, write, like you have to be able to do everything. It can kind of section off what functionality it wants to allow, but it allows writing according to the logs. If we open this and we write, I think this is how we would do it, like test. Maybe not. Nope, the issue was that it wants a byte string. Okay, let's be less crazy. Proc pwn.college. Oh, we didn't open it for reading and writing. Okay, let's just use Python's open. Open proc pwn.college f, and then let's do f dot. Let's just test reading. So if we read 100 bytes. You can see in this case that because we're using a higher level interface, it's willing to make multiple syscalls, and that's why we end up with multiple of these, but that's fine. And if we do f.write, let's just say test, because we can. We cannot, and the only reason we can't is because we didn't open it for writing. If we open for R+, which means reading and writing, f.read 100, f.write test, we can see that it returned 4, which meant it wrote 4 bytes. And now if we read again, I thought I would say something else. I am surprised by that. Hold on, let's try. I get invalid password. Yeah, I'm kind of surprised why I'm not getting invalid password. Let's try just using OS. Let's do OS read may have, I'm not sure what would have happened here, but let's see. If I do this, f.write test. There we go. Okay, this is, oh, that is actually very interesting. Don't know what's causing that. That is interesting. Huh. I'm actually surprised it does that. It's not relevant to the challenge, but huh. Cool. Well, that is an interesting artifact. I think what this is going to be like some leftover data, and I guess we didn't account for, I don't know what. Wait, I have an idea. I guess the issue is that we specified a length smaller than how much it wanted to send to us, and it's just the way that it's simply implemented is that it's going to fill 10 characters because that's how many we requested, but it's going to send back the full length of how much data it wanted to send. I'm not sure. It's a little bit of a buggy situation. I think it's leaking like a stack address or I don't know what address. It feels weird because it doesn't look quite proper, but interesting quirk of this challenge. Doesn't matter though. The next thing that we would need to do, since we already know now it's telling us invalid password, is that we would need to start reverse engineering this challenge. So the simplest way to do that is going to be to use IDA. So if we scp hacker at dojo.pwn.college and we want challenge. Okay. And if we open this .ko file in IDA, IDA will know how to look at this because it knows how to look at pretty much any sort of ELF and beyond. And it's telling us load dwarf debug information, whatever. That's some sort of debug information. We'll just go with whatever the defaults are. Little bug, whatever, we'll ignore it. Okay, we are now looking at this .ko file in IDA. And of course we can decompile it. So in this case, it starts us off in not main, and that's because there is no main function. In this case, it's looking at this bin padding function, which is kind of how we apply a little bit of randomization. It's just a bunch of random nops randomized for every challenge, not super relevant here. Okay, what we want to look at though is these device functions. So for instance, or actually maybe we want to look straight at kind of the entry point if you want to say that there's an entry point. And what that would be is this init module. It's kind of the closest parallel of main. It's going to be called as soon as it's inserted into the kernel. And this is what basically allows you to set up everything that your .ko file wants to do. So we can see in this case that it's calling FILP open flag, and all of these functions it's calling have to be implemented within the kernel. It doesn't have like libc unless the kernel is statically compiled with some libc. I'm not sure about that. I don't think that it would be, but who knows? Either way, it's calling this FILP open, which is some low-level thing for being able to open a file, and then it calls kernel read on that thing, and that's how it's kind of loading in the flag, because I guess this challenge wants to load in the flag. And then the important thing is it's using this proc create, which is creating basically the pwn.college thing, and it's specifying these fops, and that's how it's kind of creating this interface into basically what happens when I call open, the open syscall on pwn.college. What happens when I do read on that file descriptor? What happens when I do write on that file descriptor, et cetera, et cetera, et cetera. This is the full interface. So someone in chat says kernel does not include libc. Kernel has several libc-esque functions though. Yeah, that's kind of what I would have expected. I wasn't 100% sure, but yeah, that would make sense. Okay. So if we look at this fops thing, and I don't know how well IDA is going to show this to us. It seems to detect that this is this file operation struct, and it kind of okayishly shows this to us. It's not the best. We could probably just go off of function names and assume that they line up with what they should line up with, that there's not some weird trickery. There's a struct though, and this is what's defining a bunch of function pointers on. Exactly like I said, if you call open on this path, the kernel wants to redirect and say, okay, someone just called open, you're the thing that needs to handle this, and we specified device open, and this is the code that's going to handle that open operation. And in this case, we don't do anything. We just print, can we see this? Is it S? No. How do I convert you to a string? Become a string. A. Oh, I remember you just spam A's. Of course. A. Okay, so all it does is it prints out this message, which is in the .0 version. Someone said how to get there in IDA. So all I did was, I guess if we want to start real quick, just to walk through again, I was in init module. I clicked on fops, and then I clicked on device open, double clicked, and I hit tab to decompile, and then I double clicked on this thing. And that's kind of the path I took. Of course, you could just look over on the left, see device open, assume that that's going to handle the open function, which as we saw basically does nothing. But this is what happens when we call open. Alternatively, if we call close, it calls this device release function. And that just prints something. So that's kind of our open and our close. On the other hand, if we call read, we're going to have a little bit more functionality defined. So if we look at this, is there a way, I can't quite make this not be covered by my camera. There's no way to scroll. If I do this, we can see the signature. So it's taking a file pointer. So it's not so low level that it's going to be past the file descriptor itself. It's not going to be the exact same interface as the straight read syscall. The kernel is going to handle some stuff and then redirect stuff into this function. And at the point that it's redirecting to this function, it's not making you look up the file descriptor and come up with the file pointer that has the struct of the file and all this information about this file. It's just directly passing you the file pointer. But it has the rest of the stuff. So instead of an FD, it has a file pointer, but then it has the buffer, the length, and the offset. So all of this standard stuff. Actually, offset. Does read? I don't think read syscall does not have offset. I don't know if there's like a read 2 that has an offset. Or if this is just part of the interface that it's going to pass you the offset for you. I don't know if this file pointer also maintains an offset though. Maybe it doesn't. Is it the FD maintains both a file pointer and an offset, I think, maybe? Would have to look into this to be 100% sure. If, I guess, a file pointer doesn't contain an offset and FD contains a file pointer and an offset, I don't know. We'd have to look into it. Not super important though for us right now. Okay, so it prints some more debugging information, and then we have this v6 equals flag, which sounds super cool. So we want the flag. We'll call it L flag. Oh, wait, does not equal flag, or it can equal the flag. We'll say message. Looks like by default the message is the flag. According to this decompilation, I'm not super convinced of that, but there is a way for the message to be the flag. There's this device state thing, which if it does not equal 2, so if we assume it starts off at 0, because we haven't seen anything set it, we could do a little more reverse engineering if we want to be sure on that, but let's assume it defaults to 0. So So if it does not equal 2, true. So we're in an unknown state. If it's less than or equal to 2, that's also true. So it's going to ask for a password. We're just going to set message to password. This decompilation is a little not great, but we'll roll with it. And then this would be if the device state is something other than 0, which it's not. We're assuming it's 0. So we're still in this password, which means we're done. And that's why it's asking us for the password when we call read. That's kind of how this all works. And the reason probably this decompilation isn't the best is that this code is optimized. I don't remember the default optimization for kernel modules. I think it's 03. I'm not 100% sure on that. But in all past challenges, when you've been looking at a binary, you are looking at unoptimized code. We decided for the purposes of these challenges that we're just going to go with defaults, and the default kernel object build system does optimization. So suddenly you are now looking at optimized code, and I would imagine that optimized code is going to make things a little bit harder for the decompiler, because we're going to lose things that were closer resembling the source because we're optimizing. Okay. So this is why it says password. We can see though that there's other cases. So if the state is equal to 1, it tells us invalid password. I guess if it's equal to 2, or no, not 2. So if it's 0, it tells us password. If it's 1, it tells us invalid password. If it's 2, it tells us the flag. And if it's anything else, it tells us unknown state. Okay, so this is why it tells us password. And we can see that what it's doing is, the way that it's kind of returning the result is it's taking this buffer and it's copying to, it's doing this copy to user, which is kind of this safety function for effectively a mem copy. It's kind of a safe mem copy that is kind of guaranteeing that we're copying, I believe the semantics are that it's guaranteeing that we're copying from kernel space to user space. That's what this is doing. But effectively, it's a mem copy. If you want to ignore the security implications, it's basically a mem copy. So it's copying to the buffer, which is, as you all know, when you do an open syscall, you pass in a buffer. So we're passing to the buffer message v7. v7 is something basically the length of this message. Okay. On the other hand, if we look at what happens when we write to this thing, well, we can see something standing out. We can see that device state is going to be set to this optimization. Makes this a little bit weird, but if the buffer is equal to this crazy looking thing that looks like a password, the results of stir and compare in that case would be 0. Oh, but we're checking if that equals 0, and if it equals 0, that means that it'll be equal to 1, all of this, and then it'll be 1 plus 1, and that's how we get to 2. So crazy decompilation due to optimization, but that's kind of how that logic unfolds itself. So it'll set basically device state to 2 if this is the correct password. I guess this statement kind of also handles the incorrect case as well, which makes sense. Okay, so hopefully you can see that if we send this password, let's just copy it real quick. Did we copy? We did. You can see that if we do f.filenode and we just send this off and we do our read, we can see, boom, here comes our flag. So that is how we can reverse engineer this stuff. That's kind of what it looks like to reverse a kernel module. Okay, so hopefully that covers the basics for anyone completely stuck on level 1, has no idea what's going on with this new VM thing and these .ko files and blah, 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 blah. So let's see what the questions are for kind of future levels where we kind of really get into these challenges. So I know someone's interested in 9, or I guess a few people are interested in 9. what else is there? Someone is interested in 4. So they want to know how to use IO control in Python. Yes, okay. So it is a little bit less natural to use IO control in Python versus something like C, but we can do it, especially for this level, for level 4. Trying to think. I kind of wanted to demo something with pwn tools. Does it matter? Nah, it doesn't matter. Okay, we'll get to it if we have time. Let's see here. So if we start by starting our VM, we don't have to do that. We could just do VM connect, but we'll just start it. We'll just kind of show, hey, logs are happening. We can see some stuff happening. And did that print twice? Oh no, it like recolors it, doesn't it? Okay, welcome to this kernel module, blah, 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 pwn.college. Okay, in this case, you can open, close this device as you would any other file. All right, slight bug in the challenge. You can also IO control it, but the next line kind of hints at that as well. This device also supports interactions through an IO control interface. And it tells us this kernel module defines a win function which will elevate the calling process's privileges if called. So basically what this is telling us, and you would have seen this in the previous level as well, that the concept of winning has changed. The win function no longer prints you the flag, because printing you the flag is boring, even though that's kind of technically what winning still is. In the context of the kernel, the real goal, the real win case in the kernel is being able to now start executing stuff as root. That is a big win in the context of the kernel. I was executing as this hacker user, exploited the kernel, suddenly I'm executing as root. Very cool. Okay, so that's what it's going to do if we do this correctly. So if we VM connect, and I guess we'll use IPython again and kind of show IO control. I'm gonna have to do that a little bit off the top of my head, but I think I know how to do it. And unfortunately, because everything is being emulated and IPython has tons of startup code, we're sitting here for a bit waiting on it. Okay. Yeah, we have another server that we're ready to migrate pwn.college to. And as soon as we migrate to that server, we're going to have the ability to use dev kvm, which means everything will be way faster within these kernel things. But fortunately, we are putting that off for now. You'll just have to deal with waiting 10 seconds for IPython to launch. Okay, so we will import OS. Actually, we don't need OS. I don't think OS has IO control. Does it? Maybe it does. Let's see. That is really just hanging. No, it does not. Okay, but I know that there's a module called F control. And I don't know why they put it here instead of like OS, but FN or F control defines a function. Wait, what? F control. I don't know how you're supposed to pronounce that. Has IO control. So this is how within Python you could call IO control. And the interface for IO control, which this kind of matters because this is probably the first time you've seen IO control. If we do, let's just SSH in on another terminal that's outside of the VM so we can be a little bit quicker. And we do man IO control. This is the interface. So the basic gist, or at least my understanding of the basic gist of IO control is Most files, kind of the standard interface just all makes sense, right? We want to be able to read stuff, we want to be able to write, we want to be able to open and close it. Most files, you know, that's probably going to be good enough. But some special files want to be able to do more than just read and write to a file. In theory, you could implement everything with just read and write and have like a state machine that manages data coming in and blah, 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 blah. But they decided not to do that. Instead, we have this O Control Syscall. So this is a syscall. And this is basically kind of like, if you don't want to open, read, write, or close, and then there's also other things. There's like mmap, you could mmap a file. You could seek in a file. There's all sorts of other things. But basically, IO control is the, okay, I want to do something else function for files. And the way that it's implemented is we specify a file descriptor, kind of like most syscalls dealing with files. And then we get to specify a request, where request is basically a number that is defining, hey, here's the other action I want you to do, and here's how we can have a bunch of them. We get to specify a request. And then it takes in, I don't know why it's showing ... Does that mean it's optional? I mean, it is optional, but there is a third thing, which is a void pointer. Hold on, let's see. So device-dependent request code, because that's the second argument. The third argument is an untyped pointer to memory. Okay, yeah, that makes sense. I don't know why it's not just saying that here, but okay. Yeah, I don't know exactly why they do that, but it is basically just a void star. It is a pointer without a type. And the type of that pointer and how you implement or interpret the memory at that location depends basically on the request. That's why it's untyped. So for instance, in a simple case, you could just treat it as like a char star, and it could be basically a C string, and it's going to be a bunch of data until a null byte. ... means it takes multi-label args. Multi-label args. Don't actually know what that means, multi-label. So my understanding is that normally ... would mean like var args, like a variable number of args. But it just always takes a void star. That void star could be a null. I don't know. But whatever, doesn't really matter. And then it tells us an IO control request has encoded in it whether the argument is an in parameter or out parameter. And the size of the argument, argp, in bytes. The size of the argument, argp, in bytes. The request has that encoded. Well, if you follow the correct interface, this is true. I mean, in theory, you can implement it however you want, and it can be both an in and an out parameter. But I did not know this, that this is the technical interface, that the request is supposed to say kind of in or out and how many bytes this is also. I actually did not know that. It's cool to know. In our case, we don't follow this interface. We don't care. We just make it so, in our case, the request is always going to be 1337, which we would see when we reverse engineer. And we'll do input or output. I think we always just kind of take this as input, but you could see that all reversing. Okay. So, yeah. So you're the person in chat. It's the same as the printf implementation. Yeah. The variable number of args. Yeah. But I don't think you can pass like a fourth parameter. So I don't know. That's why I'm confused why it's saying this. I really don't think you can specify a fourth argument. Like everything just goes to this void star, and you can have a struct and pack in a bunch of data in there. Okay. Anyways, how do we do this in Python? This is how we can do it in Python. And I'm going to have to think off the top of my head exactly how we do this, because this third argument is a pointer somewhere in memory. And obviously, once we're working in Python, we're not exactly working with pointers anymore. But Python defines a buffer interface for getting the equivalent of that idea. Okay, so if we do, let's just try it. If we do OS open proc pwn.college, I don't think there's a mode like O control only or anything like that. I think 0 will be fine. Let's try that. And then let's say F control, IO control, and let's say FD, and let's just arbitrarily put a 42 there and run this. Operation not permitted. Do we have to specify? Does it need to be write, like writable? I am not sure on how the permissions are working here. Oops. Oh god, I hit tab and now tab is in this thing gonna take forever to resolve itself. Okay, apparently do not hit tab in IPython. There's too much code that needs to execute to make that tab work. Oh, we are just doomed. Okay. Let's try that again. os.o. We'll try saying it needs to be, well, let's try read write. And then hopefully the right part of the mode lets us IO control. I'm not super sure. Operation not, oh, you know what's happening? This is fine. This is Python interpreting us. This is all makes sense, I think. So if we look at VM logs now, we can see that we're hitting this. Okay, so the important detail is if we can see in these .0 versions that we're actually hitting this debug message, that means our code is executing or the challenge code is executing. It's no longer the Linux kernel deciding whether or not it's going to even be willing to call into this. Okay. The issue is that when we specify this command equals 42 and it's telling us operation not permitted, it's all because we're going over like standardized interfaces. And if we let's just copy this down. If I do scp, and let's look at this real quick in IDA so we can really understand what's going on. Maybe kernel level 4. Yes, blah, blah, blah. Cool, cool, cool. Okay, do your stuff, IDA. All right. Let's see here. Okay, so device IO control. If we look at this, and we can already see a password looking thing hanging out, but we'll ignore that for a second. We can see that it's saying if command, which is that 42 that we were passing before, if command equals 1337, we're going to execute this code. Otherwise, we're just going to return result, and the default of result is -1. And when this thing returns -1, I mean, we'd have to look at exactly what -1 means in the context of it, but it certainly means some sort of error. And if I had to guess, I would guess that that error corresponds with operation not permitted. And maybe you can return -2 to mean something else, -3, not 100% sure. But that's why Python is throwing this exception of operation not permitted. It's because the syscall itself returned a negative value, and based on how all of these interfaces are defined, negative value translates into this, so that in the exact same way that if I do os open /flag 0, and Python also says something else, in this case, oh yep, see, errno 1, that's probably -1, operation not permitted. But if we return -13, it would tell us permission denied. And that's how all this works, you know, it's all abstraction, interfaces, all assuming that everything is following the correct interface. And in our case, this challenge is returning -1, and that is what causes Python to do that. Okay, what if we want to actually solve this though? And since we can already see this, and you know, we're still getting familiar with the kernel in these earlier levels, let's go ahead and see if we can solve this. Using Python. In my mind, it would actually be easier to do this in C, but it should be solvable in Python. So if we do fcontrol.io control fd, and instead let's pass 1337 and we'll see what happens. Something's happening. Huh. Someone is not oh, you know what just happened? This is funny. I think I know what just happened. I think we just crashed the kernel. SSH hacker. And the way that we can confirm that, so we can see this just sitting here hanging, if we do VM logs, yep, sure enough, we just crashed the kernel. And that is because these challenges are not necessarily written caring about being correct enough, apparently. That's fine. They're all solvable, but they don't really care if you don't follow our very strict interface. We're just going to crash the kernel because they were not very safe about how we have some of this stuff written. So we can see here, when the kernel crashed, it prints out actually a whole bunch of stuff. So it is telling us, for instance, it thinks it understands what the issue is. It says, hey, bug, kernel null pointer dereference. We're trying to dereference a null pointer. And it prints all sorts of cool stuff. It prints all of the register values. It prints a stack trace. Basically a bunch of debug information that would help a developer figure out why the kernel just crashed. And we can see that we crashed inside of device IO control. And the reason for that is that this third argument, which we weren't using, gets interpreted as a character pointer, and stir compare is ultimately going to have to dereference this thing to do its comparison, and we're going to be dereferencing a null pointer, and that's where we just crashed. Sweet. Okay. That is just like, apparently that also crashes our SSH. Oh, we can hit control / to like force kill that. Okay. So let's restart. And this is kind of experience when working in the kernel. It's not quite as nice as user space. When you crash the challenge, in this case, the challenge is living inside the kernel, you really crash things. You're not just crashing a program and the kernel handles it and just kills the process. You're crashing the kernel and there's nothing handling that anymore. Fortunately, you're in a VM and the thing managing the VM we're not going to actually literally crash the CPU running the physical CPU and crash everything running on this server in a VM. That's nice, but yeah, you're crashing the whole system, the virtual system. So if we just quickly try and open IPython again, let's try and do this correctly to show how we can do this. And while we're here, let's copy, oh boy, device IO control. How do we copy this? Control C. We'll assume Control C will copy. Okay. Import OS. Open IO control. And let's pass that third argument. So in this case, let's see if this works. I think it will work if we just do a byte string here. I think Python will be able to deal with this. Let's see. Please don't tell me I just crashed the kernel again. No. Oh, Python was just taking its sweet time. Okay. Import fcntl. Okay. Wait, what happened? Oh. So as we discussed before, and actually we can see it in the logs, you win. Your current process has been elevated to root. Pretty sweet. So we're running as root now. So this process, and what it means to be, what it means when we say you're running as root now, there's, at the most basic level, everything in some sense is a process, okay? we are running this Python process. And associated with that Python process is some credentials. Credentials because of the user ID running this process, basically. So we don't suddenly like make the hacker user become the root user or something. At least that's not how this is implemented. What it means when we say we won, that you are now, your current process has been elevated to root, is that this current process that was executing as user ID 1000 and had the credentials associated with that and therefore the permissions when it comes to like reading files and stuff was 1000. What we just did is we changed those credentials to be associated with user ID 0. So yeah, so what that means is if I do exclamation mark who am I, that's how you can in IPython shell out to a process, we're going to see, hey, we're root now. So if I do os open flag 0, for instance, and then os read fd 100, boom, there's our flag. This process just got upgraded to root. Our concept of a user didn't become root. The user associated with this process became root. So for instance, if we leave IPython now, and we go back up to the parent process. So if we think about it, right, our shell was running and our shell forked off to start this Python process. That Python process got upgraded to root, but the parent process didn't magically also become root. We're still running as hacker in this case, right? So that's just something to keep in mind in terms of how these things all work. So there's a question, how could we open root shell instead from Python? So yeah, we could fork a process and start a new process, or just exec VE it straight into a new process. And that would, the way that works is it inherits the credentials of the parent process. So if our process is now root and we fork off and we're getting ready to inherit our parents' credentials, now it will also become root. So if we just give this a second for IPython to start, just to demonstrate that. Okay, so there's also a question in chat for C. Will we have to compile the code outside the VM and then run the binary in the VM? So if you wanted to run C, you could compile it inside the VM. It's just going to be slower. And since you're sharing a file system, you might as well just compile outside of the VM and then run that binary in the VM. It'll just be quicker. You don't have to do that, but GCC will take its sweet time when it tries to compile your program because everything's emulated in the same way that IPython takes forever to start up. Okay, so if we import OS, import this thing, fd equals this thing, IO control this thing, and we see who am I, right? We're running as root now. So we could do, for instance, just $ or exclamation point sh within IPython, and we can see this little hashtag, which means, hey, who am I? I'm root. I have a root shell. I could launch bash from here now. I'm root now, etc. Because everything is just inheriting its parents' credentials. So we exit out of here, exit out of here. Alternatively, we could do os exec ve bin sh empty, missing a comma. And now we can't leave this anymore, right, to go back to IPython because we just consumed this process into the sh process. But again, we have a root shell. So that is the idea. How could we open a root shell instead from Python, like from script.py? So yeah, I mean, you could do the same thing. You could just call os.execve. And assuming you didn't close your standard in, standard out, standard error, whatever, it'll all hook up into the dev tty, or it'll inherit the file descriptors as well. In the same way that it inherits credentials, it inherits file descriptors. Everything gets inherited. Okay. So that is the idea of for. Okay, I should probably... Is there any more questions, actually? probably going to jump to 9 soon, but I see a question on 7. Okay. Level 7, getting no such file or directory when calling IO control. I know my file descriptor and command are good, and I'm just passing a ret sled as the arg. Am I mixing up 7 and 9? Ret sled? No matter what I pass as arg, I get negative. Okay, let me start 7 so I can see what you're talking about. Okay, let me make sure there's not anything special here. Okay, let's VM start, VM logs, watch the kernel boot just for fun. Rather than wait for VM connect to connect, you know, we can watch the kernel boot instead. Okay, so this tells us pwn.college, you can open, close. Also supports IO control. The character device will allow you to execute shellcode inside the kernel. Like 6. Okay, but this time it's over IO control instead of write, I'm guessing. If I remember right, the previous one would have been write. It should look basically exactly the same, except you have to use IO control. I know my file descriptor and command are good. When I pass an arg, I get -1. No end. Are you opening IO control 3? How are you opening pwn.college? Are you opening it for reading and writing? Or actually, I didn't actually confirm if you needed to open it for writing or not. So we can check here. No end. Okay. And that second argument looks like strace is doing strace things. That is a 1337, I'm assuming. And then 495008. Are you using C or are you using Python? That address looks a little weird. 495008. Why would you have that address? Okay, let's look at level 7 in IDA real quick. Actually, I probably shouldn't have closed that, but whatever. IDA 7. So you're not crashing the kernel, which is good. Getting a -1 back. Which to me implies your command is wrong. I don't know if there's any other case that would return -1. So we default to -1. If command equals 1337, well, but maybe you're getting this -2. Maybe the number controls. Hold on, I have an idea. If I grep ent in user include, what is that number? That number is in fact 2. Okay, so we're getting a -2 then. That is why strace is saying ent. Which implies Oh, I might know what your issue is. Is that Arch? No, Ubuntu 2004, way better. It's not exactly the same as the previous level. It just used IO control instead of read. So if you reverse engineer this, you'll see that we dereference arg as a keyword and check if that is less than 1,000. And then when we go to do this shellcode stuff, we're looking at arg plus 8. We're looking at arg plus 8, and that's what we're copying to the shellcode. And then you can see that there's this arg plus 4104, and that's what we're calling. So it's not actually exactly the same as the previous level. It's the same sort of idea, right? We have shellcode executing inside the kernel. But you have to deal with this struct, basically. That's what this decompilation is hinting at, is that this arg thing is a struct pointer, where the first 8 bytes apparently represent some sort of size thing. And then the next, if we just convert this to hex, it'll be a little bit easier to see. The next hex 1000 bytes is some shellcode stuff. And then you can see here that the next 8 bytes is a function pointer. So yeah, it's not just shellcode that you're passing. You have to kind of create a struct, and a struct pointer is kind of the idea of this challenge. And the reason you're getting -2 is you're not passing this check, because probably you're just passing shellcode, and probably the first 8 bytes of your shellcode interpreted as a little endian integer are not less than hex 1000. Yep. Okay. All right. So I should probably look at 9 next, since I've seen multiple people ask for it or ask about it. Which is kind of strange. Oh no, I guess 4 people have solved 8. Okay, so there are plenty of people that would be looking at 9. Okay, let's look at 9. So if we do this, oh, we still haven't, okay, hold on. I want to quickly look at 8 just so I can explain it so you don't get completely caught off guard when you get here. If we look at 8 real quick, you will see that there are now 2 things here. We have baby kernel level 8.ko and baby kernel level 8, where baby kernel level 8 is an actual binary that you can run. And in fact, it's going to look a bit familiar. It's going to look like baby jail. You may upload custom shellcode to do whatever you want. Only allow certain syscalls. It opens pwn.college for you, and I'll explain why in a second. It takes some shellcode, so we'll just say P for push RAX. And then it tells us that it is only allowing one syscall. So it's like the ultimate baby jail challenge. It's unbreakable. It only allows the right syscall. You are not going to solve this by only thinking about user space. There's no way, I'm sure of it, that you can use just the right syscall to solve this. You're going to have to go beyond user space to solve this. And in fact, if we look at opt VM connect, let's just connect in, which is going to have to wait for the VM to boot. Still is like surprisingly slow. This like waiting 15 seconds for the VM to start is not the most thrilling experience. Now it's certainly much better than previous years where it would take like 5 minutes for the VM to boot. And that's because we would run a full-on Ubuntu 2004 VM. Whereas now we just compile Linux ourselves and manage our own initialization and stuff. And it's much quicker, but not quick enough. 15 seconds doesn't feel snappy. Hopefully dev KVM will change that. All right, anyways, if we look at pwn.college, where are the challenges located at? If you go to dojo.pwn.college or even just pwn.college, you will learn all about it. It'll be great. pwn.college. Okay. So we will see that if we do ls-al proc pwn.college on level 8, that unlike all of the previous levels, the other user is not allowed to read or write to this file. Only the root process is able to communicate with this file. So for instance, by cat proc pwn.college, boom, permission denied. And this is how, if you needed to implement some sort of, I mean, basically you can implement security boundaries on these character devices in the same way that you can on regular files. So for instance, if this was some device driver that was our printer, maybe we don't want literally everyone with access to the system the ability to print. Maybe we only want to allow certain users the ability to print. And that is why, just like regular files, permissions exist. And in this case, only the root user can read and write to proc pwn.college. But fortunately, we have a setuid binary that we can run. And this now inside the kernel successfully opens proc pwn.college. So that is why things are implemented in this way. Okay, there's a question that doesn't seem challenge related, but let's look at it. Got a question. Are you familiar with using MAME as VMware? Trying to get MAME to emulate running a copy of IBM 5100. Sorry, I do not know. All I know how to do is use QEMU. QEMU is, yeah, that's it. I only know how to use QEMU. That is how I implemented all of this VM stuff. But good luck. All right, so that is the idea of level 8 where we have slight differences. So when you make your way to level 8, this is something to watch out for. Okay, anyways, level 9, since that's what a lot of people were interested in, or at least 2 people. If I run, if we start by looking at /challenge, we will see that we do not have a user space binary. So we're back to not having a user space binary, which probably means anyone's going to be able to read write to it. Otherwise, the challenge would make sense. And then if we VM start, VM logs, let's see what the challenge is telling us. This challenge, blah, 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 blah. Okay, so we can open, write, and close this device as you would any other file. Good luck. Okay, so not a whole lot of information, but fortunately we know how to use IDA. And VM connects. I kind of want, in order to show this, another terminal, which means projects, pwn.college, CTF, wrong direction, CTF pwn.college, 1, 2, 3, 4, 5. Any tips on number 5 with the arg of IO control? I don't remember what 5 is off the top of my head. After this, maybe we can look at that real quick. But the simple answer is reverse engineer it. Use IDA. IDA will explain everything that's happening to you. Okay, so we've got another thing open. Okay, got this, got this. Let's just open VM logs here. And we have our challenge inserted, blah, blah, blah. So we have our pwn.college device, which is readable and writable by other users, which means we're good to go. And I just need an address. I think IDA gives it to win. Are you talking about level 5, Andrew? Address doesn't match obj dump. So if you want to know where the win function is, the quickest way you can do it, and it's going to be guaranteed to be correct, if there's confusion between obj dump and IDA and whatever else, this will definitely be correct. If you do tail proc k all sims, you're going to see, actually you need to be in practice mode, which fortunately I am, sudo tail proc k all sims. So when I just, without sudo, we can see that it's just a bunch of zeros. It's not actually telling us stuff. In practice mode, sudo tail proc k all sims, we can see all of these functions defined and their addresses where it is. So in level 9, which I currently have loaded, there's not a win function. But in your level with a win function, if you sudo tail proc k all sims, you will get the address of win. And I can guarantee that that's correct because our verification scripts use this method of getting the address of win. Yeah, so proc k all sims is actually extremely useful for all sorts of challenges. In fact, it's useful for this challenge. What do I want to show? Oh, what happens if we actually interact with this thing? So if we go back into IPython, we import OS, and we do os dot open fd, cool. And then we do os.write, and let's just do a test thing. I think we need this to be a byte string, maybe, I don't remember. os.write fd test, and we, oh, it didn't show up. Hold on, I think we need a new line. Unfortunate. We're going to see it show up twice once we add the new line, I think. Yes. Don't know why it's showing both like the black and white, or like the no color version, but then also the color version. Try VM logs again. Huh. I mean, we can see that this happens at the exact same time. Doesn't matter. We'll ignore that for now. We can see that what this challenge is implementing is this functionality which lets us write to the kernel log. So if we want to look at that, and we scp, whatever, we'll just type it in again. Hacker at dojo pwn college challenge star here. And we look at this. So someone's saying, quick question. So we wait for this to load. Blah, 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 blah. Okay. Quick question. Any hint in level 2 to get the context? The context? Oh, without read. Yeah. So level 2 is similar to level 1, but you're not going to be able to read the flag. It ends up somewhere else. Yeah. And then level 3 is also similar to level 1, but it's also a little difference there. Okay, what are we looking at here? Device write. Okay, so this decompilation looks insane. We can see this. This is like some C++ stuff. I can tell you that this challenge is not written in C++, but IDA seems to be, I don't know, maybe this means something else that I'm not aware of, but okay. Let's just ignore this. Either way, we have this p_logger thing, and we have this logger thing. And p_logger equals the address of logger, which we can see it's kind of covered by my camera, but at least this part is not. We can see that it's on the stack. It's RSP plus 0, RBP minus 120H. Okay, so we get the address of that, and then while v6. Okay, so this is some sort of loop. We'll just call this I so we're more familiar with it. I starts out at 66, keeps decrementing, some sort of looping over everything. What we're doing is we're setting p_logger buffer equal to 0. Okay, this is a crazy decompilation. It's possible the assembly would be easier to read, but everything can make sense, I guess, if we look at this. You just have to assume that it's not lying to you and just kind of look at it a little weird until it makes sense. So we're taking this p_logger buffer thing, we're setting it equal to 0, and then we're changing what p_logger is, which presumably means we're changing what p_logger buffer is. And what we're changing it to, this is just a cast, so it doesn't really matter. We're taking the current thing and we're adding 4. So basically we're going to the next 4 bytes. So basically that this is zeroing out this buffer 4 bytes at a time is the moral of the story of this decompilation. Yeah. Though we're also changing what p_logger is. It's no longer going to be the address of logger at the end. But that is fine. Okay, and then we do this print k thing. This is our debug information because we're in a .0 version. And then we have this crazy thing which says, oh, p_logger doesn't get used again, does it? Okay, so this is just like loop over logger thing. It's like kind of a pointer there as we walk over this logger thing, which seems to be our actual object that gets used later on. Okay. So what we do is we say that logger.log_function is equal to print k. So there's some sort of log function thing. So we know that logger has a log function and a buffer. And this log function thing is being initialized to print k. And then we check this. I didn't even know this would end up in the decompilation or in the code. This is sweet. This is called the kernel build system adding in buffer overflow detection stuff. How? How is this challenge solvable then? What? If length greater than 108. If length is greater than 108. Wait, I might know why, maybe. This is funny if it, huh. Hold on, what does this look like without decompilation? Is this like mixing up some order? I don't think it would be. Call. No, it does this later. Okay, whatever. We'll get back to this. What is the general logic, though, ignoring this? So we copy from user to the address of logger from the buffer for length bytes, but we've determined that the length can't be greater than hex 108. And then we call logger.log function the address of logger. Okay, does this, since it's showing this to us, is IDA doing some sort of type recovery where it's coming up with like a struct logger device write this thing? How do we view, wait, is this, we can expand this, I think. Double click? No. Oh God. There's a way to expand this. No, we're in the stack right now. We're not in the type. How do I get to this type? Structures. These crazy things. All of these letters equal E0E. Nope. Okay, there's got to be a way to view what this structure thing is. How do I expand this? Why will it not let me expand this? Okay, hold on. So this logger thing has this .log function. Where is .log function in relationship to this struct? If I hover this, offset. Okay, hopefully you can see this. I think you can. We can see that when we hover over this, it says offset equals hex 100. Oh, yeah, hex 100. Okay, here we go. Wait, are we in structures? Okay, we are. I don't know what I was looking at before. I guess it's above all of this blue stuff. We have device write this structure thing. So IDA did some sort of type recovery stuff. And it has concluded that this thing, which is a structure, has a member called buffer, and it's saying that this is 256 bytes long, aka at hex 100, 256 bytes later, is this log function thing. And this log function thing is a DQ, a quad word. So this is 8 bytes. So altogether, this structure is 100 or hex 108. So 256 plus 8. So 264 bytes long. Hex 108 bytes long. So if we look back at the pseudocode, and this is why I didn't know this was being inserted, but this is why it turns out to not be an issue, is that only if the length is greater than hex 108, so only if we go past this entire structure, it's going to do this stuff. Okay. But hopefully, since I've been alluding to my surprise that there's a buffer overflow, hopefully it's clear that the solution does in fact involve a buffer overflow. And what you're going to be overflowing is into this log function. So I guess one way to show that, if I go back here, So we can see that we can send messages, and if we end it with a new line character, it'll instantly buffer it out. If we don't, it'll wait to buffer it out. If we end it with a new line character, it's calling print k, and it's sending this out. Okay, but what happens if we just go crazy and we send it a times... start by being nice. Send 1 byte less than hex 100. I think there's... Is there going to be a null byte at the end? Oh, it's byte string, so it probably doesn't have 100. I'm gonna assume it's not appending a null byte because we're a byte string in Python. This kind of depends on what exactly Python's sending. I'm pretty sure since it's a byte string, it went null byte terminate. Okay, so if we send this, we see nothing pops up. That's because we didn't have a new line character. We send a new line character, it'll buffer it out. We can see we just sent 256 A's. But what happens if, well, there's a couple of things we can try, and I guess we'll do 2 things. So there's 2 kind of next steps from here. What happens if we send hex 200 A's? We see this. Did I just crash the kernel, or is, oh, it doesn't actually crash. Oh. It just gives up, or what? Cool. How did it not just crash the kernel? It's willing to keep going. So we can see here that buffer overflow detected because 264 is less than 512. So we just sent 512 bytes, and that is where that part of IDA is talking about a buffer overflow detected. So this is the kernel module build system automatically inserted this code because apparently it's super smart. Okay, but we didn't crash the kernel, so that's cool. I don't know, does it unload the module? What happened? How does it recover from this? No, it just has it inserted still. Is this file descriptor still valid? Did we just stop the syscall and return back to user space? Hello. Okay. Hello world still works. Okay, I guess it just gives up on the syscall and prints a stack dump and continues executing. Did not know that that's what would happen, but cool. So that is that logic. But what happens, and here's where we are going to crash the kernel, if we send 108 A's. So that is how many we're allowed to send before that buffer overflow message gets detected. And if we send hex 108 A's, we're going to see that Python is no longer returning to us. Something bad happened. And what happened is we crashed the kernel. And where did we crash the kernel? Well, we can see pretty clearly here. Since it's telling us where RIP is, we are executing at 41414141. So that's where we crashed the kernel. So we have code execution with this challenge. But I guess we can't ROP because we're not easily ROP because we would only have 1 gadget. And also we don't want, or we don't, you can ROP if you figure out how to ROP or something, but the way we design these challenges is that it wouldn't be until toddler 2 that you would be ROPing in the kernel, for instance, because this is ROPing is covered after toddler 1. But fortunately, it's not over yet. There is the magic 1 gadget sort of thing that exists in the kernel, at least given these constraints. And this is the thing that we haven't quite talked about in the lectures yet, unfortunately, but here it is. And I think we'll be adding a lecture, and Jan will also probably talk about it tomorrow. So if we kill this VM, if we restart the VM, we're going to see a magic function exists that is extremely cool. And if we do VM connect, okay, So if we sudo grep proc kalsims, and what we're looking for is this magic function, which is called run command. And this is an insane function that exists within the kernel. If we sudo grep for that, this is where it's located. And just to point out, because it might not be super obvious, but in level 10 is the only level where KSLR is disabled, or is enabled, I mean. So in level 10, KSLR will be enabled, and when you run stuff in practice mode, we disable KSLR always. So in level 10 practice mode, KSLR would be enabled or disabled, but then in the actual version of the challenge, KSLR will be on. And you can't use this trick then to get the address if KSLR is on. But for now, in this level, we can. Level 10, you can't. So what run command does, and probably the easiest way to see it, and something I guess I haven't shown off yet in these office hours, is that if we switch over into this sweet website called Elixir Bootlin, I don't know exactly what we call it, but that's what this website is. It has all of the kernel code of every version, and it has it all nicely tagged up in the ability to quickly search through the code. So if we look for this do command, and I'm searching in the top right, which is kind of covered by my camera, but you can kind of see it. If we search for this run command, apparently there's also a do command, but we're interested in run command. It will tell us what the code does, and it's sometimes really useful when doing kernel stuff to actually sit down and look at the kernel code. And in this case, what this function is it will take in as one argument a character pointer, so some string, and it's a C string, it's a null terminated string, and it will actually just go through and run a process basically as root. So it's going to argv split command. Basically what it's doing when it calls argv split, if we wanted to know exactly, we could look at the source as well. Argv split. I guess this is where the library stuff is implemented. Where argv split. Argv split. So a lot of the code is also documented pretty nicely. Split a string at white space, returning an argv. So it's basically just going to go through and at all of the white space characters, it's going to convert them into null bytes. And basically it's going to turn a C string into a character pointer, which we can see from the return type. And basically it's going to get ready to exec VE it effectively. Not quite exec VE it because that's a syscall and user space calls into syscalls, but the underlying code that does exec VE it's going to call into. So it's going to split it up, and then it's going to call this function call user mode helper, where it's passing in. This looks very similar to execve. So we're passing argv0, argv, nfp, and then in this case it has this other little thing, which if we really want to know, we can look at the source code. We can look here. We can see that other little thing, this wait variable, basically says wait for the application to finish and return status. If we do wait, if we do when, don't wait at all. Yeah, those are kind of your two options, I guess. Oh no, when, no wait. How do I look at the header? I bet it'll tell me all of our options. Yeah, these things. So these are our options. It has to do with whether you want to wait for the process to finish. Doesn't really matter. And we can see that it's going to call user mode helper setup and call user mode helper exec. And if we click on this, it's going to queue work. This work thing. I don't know, we could keep digging into this if we wanted to know exactly what it's doing, but effectively it's doing it's going to start a process. So this is going to be extremely useful for this level. It's a very useful function that exists within the kernel. run command. And also, I guess another thing to note when looking at kernel source code, if you're interested in looking at syscall handlers to kind of like what happens when I call exec VE, how does the code follow in? Obviously, you could just like step through it in GDB, or we can look for, most of the syscalls are do underscore the syscall name. So for instance, if I search for do exec VE, we will see that this is defined here in this fs exec.c. And we have this function called do exec VE. And isn't just a thin wrapper around do exec VE at common, but the same principle holds. We keep following this. This is kind of the entry point in for that. And then I guess the other thing, hopefully this is here. If we search for define, this is where the actual, like the macro that makes this stuff work is these syscall underscore defines. So we can see right here that there's a syscall define 3 exec VE, which takes these arguments and then calls that do exec VE that we searched for. The syscall underscore define 3 macro is what actually registers the syscall handler. So if we look at syscall define 3, syscall define x. Syscall define x is going to do a whole bunch of stuff, including call this syscall metadata and then underscore underscore syscall define x, which is doing this ASM linkage stuff with long sys blah 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 name underscore underscore do this, it's setting up these handlers. Basically, this is all the macro that sets up the syscall. Okay. Is there anything else we want to discuss? Are there any more questions in chat? Hopefully this is a lot of information to get you started. Zoom in or make bigger fonts. Oh, that's true. This is going to be small. Yeah. I probably should have had it zoomed in while we were going through all this Elixir Bootland stuff. But the general principle holds. Elixir Bootland, super useful for searching through kernel code. So if you want to look for syscalls, you can look for do underscore syscall name, and normally there's a function there that's defined. And then you can also just kind of like, if you were to pull down the whole code base or whatever, you could look for these syscall underscore defines. So for instance, I don't know if I can search for just syscall underscore define here. We would have to like grep through the code base. But as I said, we could do exec VE. That's going to be the entry point to exec VE. We could do write if we wanted to see the code for write. That might not be true. We might need to search for do write at. Actually, I mean, there was code there. Actually, is there even a write at? Let's see. This driver code does not look promising. What would write be? Maybe do fwrite? Do close. I don't know. You can also pull down the code base and grep for define. I don't have a super good workflow for searching for kernel code, kind of still figuring that out, but yeah, it definitely can be useful to actually just look through the kernel code to really understand what the kernel is doing. Question, what's your technique for using VM debug? Can I put a /xcc in my shellcode and continue? Will that work? I'm not 100% sure that it'll work, but I'm 99% sure that that will work. I believe that if you put a hexcc in your shellcode, have that running, that the GDB, the queuing with GDB will pick that up. Pretty sure. Okay, one last thing I guess I'll show since I don't see any more questions is how we can maybe use Pwn tools if we want to. So here is an idea. So I'm going to leave the VM. If I do, what level do I want to launch? This level's fine, doesn't really matter. If I run this code from outside of the VM, this can be a way that we can write code outside of the VM and interface with the VM, and maybe this will be some helpful, useful code. So if I import pwn, as always, context update, arch AMD64, encoding Latin, and here's some like helpful things that exist. Actually, before I go through and do this, there is a VM command that I haven't really discussed called VM exec. And what VM exec is going to do is allow you to just exec a command. So for instance, if I do VM exec ls, this is going to run the ls command within the VM, or VM exec hostname. We will see the hostname comes back with VM in it. So this can be useful if you want to script outside of the VM. You don't have to do this. You can do everything inside the VM. Just this is another option. So what we might want is maybe a function called run with a command. And what we will do with this is we will do with pwn process. And the process we're going to run is we're going to run VM exec command here as process. Actually, we don't even need to do this with. Let's just return that. Now, if we just do run hostname and we have this pwn tools thing now, like for instance, we can do read all on it. And now you can kind of use pwn tools from the host and start interacting with the VM. Might be useful. Yeah, so that's kind of an idea. Another thing you might want that, so I'm just kind of basically demonstrating some things that we have in our verification code. Maybe you like this, maybe you don't. I also have something called runC, which takes some source. And what we do is we do with open temp runC write f.write source and then we need, we'll just take subprocess also, import subprocess and subprocess run gcc -o temp runC, and then what we would do is we would do return run temp run. Yeah. So then what we could do is we can do runC, and we can do a multi-line string. Now we can do something like, for instance, int main printf hello world. We forgot a colon. And if we run this, we will see it prints out, oh, we forgot it, as f. Oh, we forgot to do runC read all. Boom. So we can see, for instance, now we get this output of a C program running inside the VM. So this sort of template might be useful for you. Maybe you don't care about this, just something to consider. And the reason you might want C source code is because it can be easier to do stuff like IO control and that sort of thing when you can just like define a struct. So for instance, we could do like struct challenge, and maybe we say like UN64 length car buffer void pointer include standard int.h. And then we could do like open pwn.college 0 print fd equals this, printf fd this. And what else do we want? And then like IO control fd 1337 and like struct challenge length equals 2000. Good enough for now. And we just pass the address of that struct. Int results. Printf result the result. Cool. And assuming this compiles, we will now be running, and it does not. We're missing some semicolons, aren't we? Where? Oh, you know what the issue is? So it's a little bit weird to write C within Python. You need to do double backslash, because otherwise it's going to get interpreted as a new line character and it's going to mess up our source code. Challenge undeclared. Challenge. Oh, we'd never named this thing. Challenge. Did not compile. Got a semicolon somewhere. Where is our missing semicolon? I'm not seeing it. Expected semicolon. Hold on, here's what we can do. We do cat temp test.c. What are we calling this? Run.c. Semicolon. Do we need a semicolon there? You might be right. Sounds believable. Clearly I don't write enough C. All right, yeah, it looks like we needed a semicolon there. Okay, so fd3 result -1. Maybe we like just decode this so it'll print itself correctly. Will it print itself correctly? I think we still need a print. Whatever. Result -1, which makes sense. Because we... Would it be with -1? I don't know, but here's the basic idea. You can start messing around with this. Why is it -1? I was expecting -2. It's because this IO control wrapper is converting everything into -1s and doing an error no. How do I get an error no? Can I do that? That doesn't look right. Maybe it is. How to send address in IO control. So this is approximately how you would do that. Do I need to include error no? Include error no. Is this correct? Oh, it is. Maybe. 25. Did I already look at, so someone's asking about level 5. Did I already look at level 5 in IDA, baby kernel? Level 5, I did not. But for instance, the way that you could, if you wanted to just send, in fact, I think we would need to include let's see, include, I think we need this to make sure that our IO controls aren't going crazy. We wanted stdio as well. Let's just make sure we don't have warnings because otherwise some type stuff can get crazy. Missing open, missing IO control. Where are these things defined? Man, IO control. Sys IO control. Sys IO control. Okay, go away warning. And I think we need that, otherwise it's going to start interpreting stuff as 4-byte integers rather than 8-byte. Man to open. I'm missing F control. Okay, it's compiling correctly now. If I make this be a valid size, will it stop returning -1 there? Still getting a -1. Hold on, we can quasi-debug this if we look at the logs. Oh, we're missing, we don't have permission. That's the issue. Oh, read write. Pretty sure that's the issue. Re-looking at VM logs. So we can see that we're opening and we're closing, but we don't see device IO control. Wait, what level are we on? Do we have an IO control on this level? What are we on? Are we on 9? We're on 9. I don't think 9 has an IO control. That is why this is failing. Okay. Let's switch over to level 5. And yeah, I talked about 9. I'll put it in chat also. 5. Someone was asking about 5. Let's look at 5 real quick. That way we have an actual IO control. And then I'm going to start wrapping up these office hours because we have definitely gone late. Let's wait for the VM to start. Oh, did I lose my IPython history? Oh no, I exited. Okay. Cool. IPython. VM logs. All of this code. What? Oh, we're crashing stuff. That's why. It probably makes sense because where's our IP? Unable to handle page fault for address blah. Kernel tried to execute NX protected page. Yeah, that's because the way I have this set up. But there was also a question about like how do we just pass an address? So for instance, I mean, you could just pass what would be the way to do this? If we cast to a void pointer and we just say like 0x1234, this will be passing 1234 as that third argument, which is also going to crash the kernel, and it's going to take a bit for us to boot up. Oh no, because we're just crashing. We're going to crash again because it is going to try to dereference 01234 in the context of this challenge, but that is how you could just pass an address if you wanted to literally just pass an address here. Maybe you need struct stuff, and yeah. Okay, all right, I am going to wrap up this office hours. I think I covered a lot of things related to the kernel. If there are more questions, as always, feel free to ask in Discord, and we will have also Jan's extended Q&A tomorrow, which I'm sure we'll be able to discuss all sorts of more things related to this. All right, thank you everyone for watching my office hours, and see ya.